now that we understand the different definitions of matter and what comprises matter, we're going to take a look at atoms. So remember, these are the building blocks of chemicals. This is a nice example of what an atom kind of looks like. So something that I really liked about this image is that it shows you that atoms are moving all the time. They aren't stagnant. This is a really great picture of one. They're constantly vibrating, and the electrons are zooming around the outside of the atom very, very quickly. And so this is a good example of what comprises pretty much all of the things in the universe. So you can kind of see this entity in motion. All right, so what's inside of an atom? These things that make up our elements and our compounds and our mixtures and all of our substances and all of our matter. We're going to look at the different things inside of these atoms, okay? So if you would like to do this, there's an app called atom.phys that's really, really cool. And we're going to use it for this class to demonstrate what atoms look like and their different trends. So go ahead and download atom.phys for your iPad. It's free. Let me open it here to show you what it looks like. It's this icon right here, this little dot right here. You can kind of see it down to the right. Right. So this is a really nice app to use in order to visualize the different particles inside of atoms. So we're going to go to the modeling. And if you look here, this is a fun little thing to play around with. You can add electrons and protons and neutrons. These are the different building blocks of atoms, what we call subatomic particles. So I'm going to go back to the slide, and it's going to have all of these definitions on it for you. So you can add electrons, right? And you'll notice that as you add electrons and protons and neutrons, this thing will grow and it will change. And so we're going to use this to model some substances. So this menu up here in the top left, if you click on it, you can choose all the different atoms in the periodic table. It's really cool. And you can click on one and it'll just automatically populate electrons, neutrons, and protons for you. You can make this bigger or smaller. You can stop it from moving if you like, or leave it moving. Okay, so let's use this to explore some properties of atoms. Let me go back to our PowerPoint slide here. All right. So subatomic particles, let's take a look at what these are. We have different components to our atom. We have our protons right here. These are inside of our nucleus. So this is a very important term, nucleus. This is the dense core of an atom. And it comprises our protons and our neutrons. So that's this thing right here. And it's got protons and neutrons inside of it. What's unique about protons is they have a positive charge on them. So if you've ever had a magnet and you've noticed there's like a north and a south pole, right? And they push and pull on each other. Atoms have subatomic particles inside that also push and pull on each other. So just like a magnet, this proton has a positive charge. And what's unique about a proton is it's pretty heavy. It has mass. Now, another type of subatomic particle, here's this term written out for you if you need to see subatomic, is an electron. These electrons are the things that zip around the outside of the atom. So these are the yellow things right here. Those are your electrons. And these have a negative charge. So they're the opposite charge of the protons inside. So there's a lot of pulling and pushing and stuff that's going on inside of our atom. And what's unique about electrons is they're lightweight. They relatively have no mass. So relatively no mass. So when we're considering them in regards or in comparison to protons and then also our neutrons, which is our next type of particle, they essentially have no mass in comparison. Neutrons are the other thing that is inside of our nucleus in here, and they have no charge, They are neutral, thus their name, neutrons. They are also heavy. They have mass. So these different numbers on the periodic table correlate to the different types of subatomic particles inside of the atom and how many that there are. So remember that protons and neutrons have mass. So when we look at the periodic table, guess where the mass number comes from? These particles. So down below, let me use my blue. Oh no, go back. I want to use my blue pen if I can. Let's see here. Okay, so blue pen, we see here this number down below. This is our mass number. I don't know if you can see this. This isn't the greatest. It's a standard atomic weight. That's what that symbol is there. You might also hear me refer to it as average atomic weight, or atomic mass. Sometimes those get used interchangeably, even though they technically are not the same thing. Okay, so the mass consists of your neutrons and your protons, because electrons don't have mass. And then this number up here on the top, this one indicates the identity of our atom, and that's indicated by the protons. So this is our number of protons. And in atoms that have that come directly from the periodic table without alterations, so they're in the form that they are in the periodic table, that's also the number of electrons that they have. So we can model this in atom.phys, and you can see that. So let's go to our helium here. So I'm going to model helium. If you take a look in our helium, you can see we've got 2 protons, 2 neutrons, and 2 electrons. So 2 of everything. And when we go back to our periodic table, we can see that reflected in the numbers. So up at the top, we see our number of protons is 2. We know that our protons are equal to our electrons, so there's 2 of those. This mass number is neutrons and protons. So this is mass is protons plus neutrons. And if there's 2 of each, that means there's 4 total. And we see that reflected in the mass number of 4.003. Okay. All right, so remember that this is your number of protons. It's also your number of electrons. In most cases, we're going to discuss when that is not the case. Usually, number of electrons. You might see me abbreviate electrons sometimes in this class as E minus, because they have a negative charge. Right. And then this here is our number of protons plus neutrons, because these have mass, whereas our electrons do not, and do not contribute to mass of the atom. If you'll notice as well, something that I really wanted to point out, this is a good example of a realistic atom here, this picture that's drawn. You can see the nucleus here, and you can see the electrons around outside. Now, in reality, the protons and the neutrons are much bigger than electrons in this model. I think that's the one thing that's not very accurate. So protons and neutrons, in comparison, like a proton might be this big, and an electron is itsy bitsy tiny, okay? They're usually much smaller, but this distance from the nucleus is correct. These electrons are quite far from the nucleus the majority of the time. And what's interesting that you'll see about this model is you see kind of like there's a blue shell around the atom, and then there's a purple shell. And you see that these electrons are traveling in circles around the atom. And you'll notice they have different paths, right? We call these orbitals. Each electron has its own unique orbital that it travels around the nucleus of an atom. These are certain paths, and they reside in different shells. So something that you'll see whenever you go to model things in your atom.phys is when you choose some of these bigger atoms, So boron here, slightly bigger. You see that there's one shell, and then there's another shell of electrons. As you add more and more electrons, this one's 2. So we see 2 here. Let's go down to an even bigger one. How about an iron? We talked about iron. Let's check out what iron looks like. Wow, okay, so it's got 4 shells. You can see the electrons, 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 and electrons. So these things are located in specific orbitals around the nucleus of the atom. Okay, so now I'd like you to answer a practice question about these. I'd like you to use the periodic table, okay? You're gonna need to use the periodic table for this, not atom.phys, in order to figure out the number of protons, electrons, and your mass number on the periodic table for hydrogen, nitrogen, and sulfur, okay? So you'll wanna pull up that periodic table that I said you're gonna need earlier, and you're gonna want to figure out how many of these different subatomic particles are in here. If you'd like to check your work, you can model them in atom.phys afterwards. I would recommend it, just so you can check and see if you did it right, and do your best to answer this question. Okay, so you might be wondering, now that we've looked at what an atom looks like, why electrons go in these shells. Okay, so why do they have orbitals? Why are there like 2 on the inner shell and then like it gets bigger and bigger and bigger? This is not magic. This is a property of atoms that I'm not going to cover in this class because it's a more advanced concept than we're going to discuss. But I do want to briefly just touch on it so you understand where it's coming from. This is actually from quantum mechanics. So the quantum mechanics dictates how our neutrons, protons, and electrons interact electronically. So how they're repelling each other, how they're magnetically interacting as well. So think about, again, the magnet example. The North Pole attracts the South Pole, right? If you switch the ends, then they'll push each other away. Atoms, all these particles inside are rotating, they're vibrating, and they have different pushing and pulling on each other. And so quantum mechanics is a way to describe this. And it tells you, once you do the calculations and things, it's going to tell you how this works. And the reason essentially it does this is because atoms want to adopt the lowest energy state. So they want to adopt a configuration where that pushing and pulling is at a minimum, everything's stable and steady and neutral. And so by putting electrons in the shells, it just makes it more stable. So nature in general just likes to do things that are energetically favorable, as in stable. So just know that's why that happens. Again, we are not going to cover this, but there's a lot of really cool applications of quantum mechanics. Particularly right now, a hot topic is quantum computing, where they're actually using atoms and electrons, and they're using this in computing technology to make like super duper high speed internet. It's a really cool thing. So if you have questions about quantum computing and you want to know more, here's a nice little website down here that actually describes a bit more about quantum computing. If you'd like to pause the video and type that into your browser so you can read about how it works. Okay, let's take a look at another trend that we observe in the periodic table. So you'll notice that the periodic table has all of your elements lined up, right? They're all lined up, they're in rows too, and they're that way for a reason. They aren't there randomly. These are put there systematically. And so something you're going to notice is that as you go across the periodic table from lithium, you can see this lithium over here, to the other ends, to your neon, as you proceed this way across the periodic table, your group number, that's this here, this is a group number, increases. And you'll see it goes up from 1 to 18, increases. Your group number dictates how many electrons are inside of your valence shell. Okay, and I'm going to tell you what that is in just a second. Okay, so here all of these elements in this first row have one electron in their valence shell. These have 2 electrons. Now, this says 13 here, but we're going to skip the transition metals. These have 3 electrons, 4 electrons, 5 electrons, 6 electrons, so on, 7 electrons, and 8 electrons in their outer shell. You can see this when you model things in atom.phys. Okay. So what are valence electrons? Valence electrons are electrons that participate in chemical bonding, being sharing or transfer. So they transfer electrons to other atoms, or they might pull in electrons from other atoms, or they might share them equally with another atom in order to create a chemical bond of some type. These valence electrons are typically electrons that are in the outermost shell of an atom. So let's take a look here at fluorine. So let's go in here to fluorine. Let's check out our fluorine. All right, so fluorine on our periodic table was in group 7. Let's see how many electrons are in its outer shell. If you can count here, we got 1, 2, 3, 4, 5, 6, 7 in the outermost shell. You'll notice there's 2 more on the inside. So on the periodic table, if you look, fluorine has 9 protons. It's number 9 on the periodic table, which means it has 9 electrons, but it only has 7 in the valence shell, in the outermost shell. And those electrons are special electrons because they are the ones that are able to participate in chemical bonding. And that's where the magic happens, is chemical reactions. So whenever you see a chemical reaction, it's coming from those electrons specifically. And so they have similar chemical reactivity, chemical activity to other ones in its row because they have the same number. All right. So let's take a look here at the period as well. So this is what we called our group number when we go across this way. That's the group number on the periodic table. This is our period. Periods increase going down. So this is period 1, period 1. This is period 2, period 3, period 4, so on, so forth, period 5. And what this means is it's going to indicate to us how many electron shells there are. So our hydrogen and our helium only have 1 electron shell around them. But then when you get to lithium and beryllium, you get another electron shell, right? So now you've got a second one in that second row. And then you get to sodium and magnesium, and you get another one. It gets bigger and bigger and bigger and bigger, okay? All right. So let's take a look at this here. So fluorine, we just modeled fluorine, right? It had 7. So let's take a look at chlorine. It's the next one down. Fluorine, chlorine. Let's see, should be right. Oh, further down. There we go. All right, let's let it populate. There it is, 3 electron shells. Yet, if we look in the outermost electron shell, let's see how many electrons there are. There's 1, 2, 3, 4, 5, 6, 7. 7 electrons around the outside, but it's got 3 shells. And if you count the total electrons, remember that's the number on top of the chemical symbol, we're going to see there's 7 plus the next ring, which is 6, 7, 8, 8. So plus another 8 plus 2. So we've got 10 plus 7, which is 17. And if we look at our periodic table, our chlorine, that's where it's going to fall. It's number 17 on the periodic table. So that's how many protons it has as well. Protons and electrons are included in that number.